equals x plus 1, I'm replacing my whole output with 2. So that entire thing, f of x, is 2. And that is equal to x plus 1 because I don't know what x is. One challenge of this whole function notation thing is getting comfortable with the idea that like f of x is sort of like a single variable. Like f of x has a single value. It's not like two separate things. So f of x represents the output. So the whole thing I'm replacing with my output of 2, and then we solve the equation. We get x equals 1. And we can see that on our graph, too. If I have a y value of 2, that corresponds to a point on my graph with an x value of 1. Does that make sense? I know you had one on your homework where it like gave you like c of x equals 10,000. Yeah. And so you want to be really careful. And the easiest way to tell if you should be plugging a number in for x or not is like if you look at the function notation, if there's not a number here, then you can't put a number in for x because you don't know what x is. Whereas like here, we're given a number for x. And so that's how we know we're replacing x as opposed to setting our function equal to a number. Make sense? Questions? Okay. Let's do another one. Let's let g of x be the function actually that shouldn't even say g of x, it should say g. Be the function defined by the rule. Multiply by 1/2 and raise to the third power. So I'm sure you talked about this yesterday. When we're given a function in words, the order matters. So after I do an operation, the next operation is done to the result of what I got the first time. So once I multiply x by 1/2, I'm going to raise the entire thing to the third power, because otherwise it would say raise the input to the third power, then multiply by 1/2, right? So if, see, part A, we'll write g of x in function notation. So g of x, as soon as I write that, I have decided what I'm using for my input. Like if I had written like g of t, then that means that the variable in my formula on the right side would have to be t. So it doesn't really matter what that variable is, but you have to be consistent. Like what's in the parentheses on the left has to match the variable that you use in your formula on the right. So when I wrote g of x, I decided that x is my variable. And so I'm going to multiply that by 1/2. And then cube it. So everything I got after I multiplied by 1/2 is being raised to the third power. As opposed to if I did my input to the third power times 1/2. Right? So the order that those operations are given in affects the value of the function or the output. And in this case, I would just leave it like this. We get really hung up on simplifying because it's often necessary to simplify. But here, like when I look at this and I think about plugging numbers in, I think it's probably easier to just multiply a number by a half and then cube it, because then I have smaller numbers to deal with, than cubing the number and then multiplying it by an 8. So I'm not going to worry about simplifying that to get rid of the parentheses. I'm just going to leave it like that. So let's graph. Y equals g of x. And again, when I look at that, I see that there's an exponent, and so it's not linear, but I don't really know the general shape of the graph. So I'm going to do at least 5 points. And in this case, when it comes to picking x values, like I said earlier, like if I don't have a reason not to, I use -2, -1, 0, 1. But here I see that I'm going to multiply by a half. So like, why not use even numbers so I don't end up with fractions, right? So just because it's convenient, there's not like a right or wrong x value to choose, but you might as well make it as easy on yourself as possible. So maybe -4, -2, 0, 2, and 4. As a general rule, it's always a good idea to use 0. Kind of anchors your graph. So -4 times 1/2 is -2. Raised to the third power is -8. -2 times 1/2 is -1. Raised to the third power is -1. 1/2 times 0 is 0 to the third is 0. 1/2 times 2 is 1 to the third is 1. And 1/2 times 4 is 2, raised to the third power is 8. So I've got my points. It's 1, 2, 3, 4, 7, 8, -2, 1, 0, 0, 2, 1, and 4, 8. And so it's clear from what we've got so far that it's not going to be a straight line, right? There's no way to draw a straight line between all those points. So if it's not a straight line, we say that you're going to draw what we call a smooth curve. The word smooth actually has mathematical meaning, incidentally. But a smooth curve through the points, which essentially just means no straight lines and no sharp corners. So just like it sounds, just a nice smooth curve that passes through the points. Doesn't have to be perfect. I am by no means good at drawing these without wobbling all over the place, but do your best to show that it's not straight lines and get through all the points. And as we keep going, you'll get to know the general shapes of what we call the parent functions. We're going to go over those on Monday, but you'll get to know, like, by looking at the function, like sort of what the general shape of the graph should look like. And so it won't be like you're flying blind. But for now, just go ahead and do the 5 points and pass through them. Good stuff? Okay. Let's find the net change in G from x equals -2 to x equals 8. And now that we have a graph, I just kind of wanted to show you like how net change corresponds to like the graph on the function. So when we're asked to find the net change in G, we're looking for the change in the y values. So we're saying if x is -2, I'm down here. And if, I'm sorry, that's supposed to be a 4. Otherwise I couldn't put it on my graph. And if x is 4, I'm up here. And so when we ask for net change, we're saying when I move from the leftmost point to the rightmost point, what happens to my y value? So we're really just looking for this distance from here to here. And we always do rightmost minus leftmost, right? So just like when you calculate any other change, like you do later minus earlier, right? Like if I had $5 yesterday and I have $20 today, and I want to know how much my account balance changed, I would do 20 minus 5, not 5 minus 20, right? So later minus earlier, we're doing G of 4 minus G of negative 2. And instead of calculating those again, we can just use our table, right? We see that when X is 4, my output is 8. So G of 4 is 8. And when X is negative 2, my output is negative 1. So G of negative 2 is negative 1, which gives me a net change of 9. Which we can see on that graph as well. If you count up from that point to that point, you see that it goes up by 9 units. Which reminds me. I want to look at your sentences here real quick. Very good. So when it comes to these sentences, sometimes it can be hard to figure out exactly what we're looking for. So all of your sentences look awesome in that you didn't have math symbols in them, right? So, which is perfect. When you're giving a sentence in context, you always want to talk about the context of the problem as opposed to the math symbols that you used. So the three things I look for, because they can be worded a bunch of different ways, but the three things I look for is that you say how your input is changing, and then you say if your net change is positive or negative somehow, like increases or more or whatever. And then that you have your units on there. So those are the three main components I look for in the sentence. And then the way it's worded can kind of vary. But your guys' all look great, so we don't need to talk more about that. Okay, you guys try this one. So let's let f of x equal to x squared plus, minus 9. Have you graph it. Evaluate. Go ahead and do all those. So one thing that came up a couple times was parentheses. So if there's no parentheses in the original statement of the function, then the only parentheses you're going to put in are the ones that you put your input in, right? And you need those to get order of operations correct. So when you plug in negative 2, you've got 2 times negative 2 in parentheses squared. So f of negative 2 is 2 times negative 2 squared minus 9. So you need parentheses around your input, but you don't want to add any more parentheses in that function, unless they're already there. So I think that this ended up looking like yeah. Curve through that. And then let's evaluate. So when we evaluate f of a, all that's saying is apply the rule to an input of A. So if my rule says f of your input is 2 times the input squared minus 9, then f of A, my input is A. So 2 times my input squared minus 9. And that's all. And then for C, notice that that H is not inside the parentheses, right? So all that's saying is write down what f of A is and then add H to it. So you're adding H to the output that you get after you evaluate f of A. So f of A plus H, well, we already know what f of A is, right? Because we found that in part B. F of A is just 2a squared minus 9. That's the output if I input A, and then I'm just adding H to that. So if it's not in the parentheses, we're just tagging it on to the end. We're applying it to the output. And then when we solve f of x equals 9, well, we have f of x equals 2x squared minus 9. And that's saying f of some input gives me an output of 9. So I don't know what x is because I'm not given the input. I'm not given what's in those parentheses. So I'm replacing this entire thing, my entire output, with 9. So when we have f of x equals 9, they're saying set your function equal to 9. As opposed to your input equal to 9. So 18 equals 2x squared, 9 equals x squared. And we haven't gone over how to solve equations like this, but we can kind of think it through, right? All this equation is asking for is any numbers that you can square to get positive 9. So what numbers can you square to get positive 9? 3. And negative 3, good. Is that okay that I got 2 different inputs for a given output for a function? So it's okay because I have 2 inputs going to the same output, not 1 input going to different outputs, right? So remember, functions have to pass the vertical line test, which this one does. When I get these 2 points, I didn't draw my graph very well so that it actually goes through those points, but they're like right here and right here. So I'm not violating that vertical line test. It's kind of like if we all went on to the airport and took a plane somewhere, we could all get on the same plane to go to the same destination, but one of us can't get on 2 separate planes at the same time to go to 2 different destinations. So far, so good. Questions? You guys are quiet. Because this makes perfect sense. Yeah. Let's do one more. We're going to let f of x equal 2x minus 3. Evaluate f of A. And whoops. F of A plus H. And then we'll find the net change. In f from x equals a to x equals a plus h. Okay, so just like the previous problem, if I'm evaluating f of a, it's just saying apply that same rule to a instead of to x. So f of a equals 2a minus 3. Now this next one, notice that what's in the parentheses is a plus h. So a plus h is my input, as opposed to what we did on the last one, where what was in the parentheses is just the a and we're adding h to the output. So this one, we're adding a to the input, or sorry, h to the input, and applying the function to that. So my function says multiply by 2 and subtract 3. And my input is a plus h. So I'm going to multiply my input by 2 and subtract 3. You want to think of that a plus h as like a single value, even though it doesn't look like one, because it's what's in the parentheses. When we read f of a plus h, it says find the output associated with an input of a plus h, because that's what's in the parentheses. And we can simplify that a bit. 2a plus 2h minus 3. And now we're going to find net change. So it looks a little different when there's not numbers involved, because we don't feel like we get to actually subtract. But the process is exactly the same, right? Later minus earlier. So we're going to evaluate the function for the bigger x value and subtract the function evaluated for the smaller x value. Now I can't subtract, I can't do like a plus h minus a and then plug it into f, because of order of operations. That subtraction is happening after I apply f individually to those inputs. So this isn't the same as like f of a plus h minus a. We can't just like distribute like that. So rather than doing more work, always use what you've done if you can. So we know what f of a plus h is, right? We found that in part B. So I'm just going to replace f of a plus h with 2a plus 2h minus 3. And I use parentheses there because remember that 2a plus 2h minus 3 is a single output. So we want to think of that, just like we thought of the a plus h as a single value, we want to think of that 2a plus 2h minus 3 as a single value, because it is the output that I get when I plug a plus h in, even though it looks like three separate things. And then we're subtracting f of a, which again we have from part A. We know that f of a is 2a minus 3. And again in parentheses, because we want to think of that 2a minus 3 as like a single value. And that's what parentheses do for us. It groups an expression so that it represents a single number. And then to simplify, I notice that I don't really need that first set of parentheses because there's nothing in front of them to distribute, right? So we can just drop those. But to get rid of the second set of parentheses, I have to distribute that negative, right? You can think of it as like distributing a -1. So this is minus 2a plus 3. And if we combine like terms, we get 2h. So what we did here is the beginnings of what is called the difference quotient, which is the basis for the definition of a derivative. So, which is basically what your entire first semester of calculus is based on. So we are going to work on just the algebra of the difference quotient, like simplifying it and evaluating it so that you guys are really good at that piece of it before you go to calculus and have to worry about the meaning of it too much. So that's why we're doing these kind of weird looking things, is we're building up to that difference quotient, which we'll talk about here in a few days. Questions? Okay, well, we went quick. You guys want to try one? I think that's a good idea. We should do one just like this. Okay, so we had f of a equals negative 4a minus 9, and f of a plus h equals negative 4 times a plus h minus 9. H minus 9. So far, so good? And then when all was said and done, f of a plus h minus f of a was negative 4h. I think that's what I saw in everybody's paper. Is that what everybody got? Does anybody want to see the details? Do we feel good? Okay. Very good.